So let's get started. So this is a talk about causes and effects in the microscopic world. It's mostly a foundational talk. It's a topic that is not yet very practical and very oriented to real applications that we have nowadays. It's more like building the foundations for future technologies and future applications. So the ideas will be the key part, and then I will tell you a bit more about algorithms. Let me start from the kind of the very basics of causes and effects. This is really what it means in the everyday life sense of the words. Cause and effects are like the ability to influence some variable based on some other variable, that is the one that we can act on. And understanding when there is a cause and effect relationship is extremely important, both in science, in technology, and in our everyday life. I mean, going very popular here, some of the questions that you may be familiar with are like, what are the causes of global warming? Is it due to some human activities or to some fluctuations in the Earth environment? Like, how can you distinguish between these things? Or, for example, in genetics, you could ask which kind of genes are responsible for a certain hereditary condition, and like what kind of techniques are you going to use to establish this causal dependence between one variable and another? So here there is, well, this image that I took here comes from a competition that was organized by a computer science conference, and the title was Causality for Climate, which was pretty much like a competition on developing models, causal models for different aspects of climate. And the way that you normally do it is starting with some graph where you put the variables and you put these arrows when you believe that there is a dependence between one variable and another. Now, let me start from the very basics of what people would learn when they learn about causality, the causality 101. You might have heard this motto that says, correlation does not imply causation. So just the fact that two things are correlated with each other, that they have correlated values, does not mean that there is an actual causal dependence. Here there is a classic example, is the example of two variables, the reading ability of children in primary school, maybe measured by the level of books that they can read, like 1, 2, 3, 4, 5, and the foot size. Apparently, these two variables are very strongly correlated with one another. So does it mean that if you have a bigger foot, you can kind of read better? There is some magic causal dependence of your abilities from the foot? Well, no. Or at least we don't believe so. Why do you think that these two variables are correlated? Anyone? A coincidence. It could be a coincidence. Well, a simple explanation is that the age of the elementary school kids is correlated both with the size of the feet and with their growing ability to read. So yes, it's natural to expect that there is a cause-effect relationship from the age of the kids, which means that if they are older, they will be probably able to read better, and also their feet would have grown more. So the correlation between these two variables is just a correlation. There is no causal relation between this and this, but there are underlying causal relations from the age to both of them. So here there is a causal dependence. The age is a factor that controls both of these variables. The correlation itself has no causal meaning. There are lots of examples like this, including pretty funny and crazy ones. There is a website that collects all the strange correlations, some of which are accidental, as you said. Like, I guess this is an accidental one, the rate of divorce in Maine with the consumption of margarine. So probably there is no relation, at least no direct relation between how much margarine you eat and your tendency to divorce if you are in Maine, but there are pretty strong correlations, at least in this series that was analyzed here. So the moral is that statistics on the correlations is not enough to establish causal relations. So if that is not enough, what is enough? So in order to establish a causal relation, at least in principle, we should have some ability to tune the values of one of the variables, not just to observe the correlations, but to check, to change the value of A, of one variable, and see if changing A, we have some change in the variable B. So if we have, so we need to have a knob on A, the ability to change the value of A at our will, and to check then if the statistics of B is changing based on that. So this, at least in principle, I mean, maybe it may be very hard to really change the value of A, but at least in principle, we should conceive the possibility of changing the value of A and testing different settings for the value of A. So here is a bit more a mathematical distinction between the two things. When you talk about correlations, you talk about the joint probability distribution of two variables. You just check what is the probability of A and B together. When you talk about causation, you're talking about a process where A is the input and B is the output. So here, this is a conditional probability distribution of B given A. There is no prior probability for A. You just change the value of A depending on your choice. So the primary object when you talk about causal relations is this process, is the conditional probability distribution. Whereas when you talk about correlations, is the joint probability distribution. So here graphically I represent this as this thing with two wires in parallel. And here instead there is an input on the left and an output on the right. Okay. So the main hero in the classical world for causality is Giulio Pearl. He developed a rigorous mathematical theory for causality in the 1990s with his collaborators. So the idea here was to build a mathematical and algorithmic framework for discovering causal relations. So for defining and discovering causal relations. And to develop algorithms that would do this automatically, that would discover causal relations automatically. So he has all this graphical framework with graph, using a lot of graph theory, and then algorithms that can test the dependencies of one variable on another. This is a classic book. Is this a real textbook that if you're interested, you can look at? Well, Pearl got the Turing Award for this in 2011. A Turing Award is like the Nobel Prize for computer science. So he got this for Bayesian system and for causality. And here the motivation of the Turing Award. So he got this development of a calculus for probability and causal reasoning. And this was has been transformative within AI and computer science and had impact on economics, philosophy, and other disciplines. So the idea here is that this work by Pearl has been very influential and especially has found application in classical artificial intelligence. This is instead is not a textbook, this is a popular book. And if you are looking for something more interesting to read during the Christmas vacation, you could have a look at this. So now coming to the topic of this talk, how would it be to test cause-effect relationships in the microscopic world when we have small systems that obeys the different laws of quantum mechanics? All the work by Pearl and his collaborators is based on classical statistics. So all the algorithms that they have are classical algorithms, but they just don't work when you go to the level of quantum systems and quantum particles. Because when you go to the level of the microscopic systems, we have different phenomena, different laws of physics. Most importantly, you have things like interference, so that certain variable would have a kind of show some interference patterns. So this is called the coherence. And another feature that is called entanglement, whereas you could have two particles that together are in a well-defined state, but individually are not in a well-defined state. So it's like two particles that are married to one another in such a way that they are well-defined if you look at them together. If you look at one alone, is completely indetermined. So this phenomenon of entanglement leads to another feature called non-locality that prevents the application of Pearl's algorithms to quantum systems. So basically, all our theory of causality is classical and doesn't work when you go to the microscopic level. Sorry, just to know how much time do we still have? All right. Just, all right. So the big question now is like, what is a cause-effect relationship when you go to the level of quantum systems? And how would you discover it? So how would you discover a cause-effect relationship in the microscopic world? So first question, the second question would be, why would you even care about this? I mean, I personally care for fundamental reasons. I mean, I want to have a notion of cause and effect that is defined even at the most fundamental level, because the world is made of quantum particles. If I want to talk about cause and effect, I would like to be able to do it even in the most fundamental layer of physics. But there are even more practical reasons to look into this. The main reason for me is that in the past few decades, 3 or 4 decades, there have been major advances in quantum engineering. And what does quantum engineering mean? It means that we now can engineer some individual quantum systems and probe their interactions. So we have a lot of devices that are called quantum devices, like we had the transistors for many years before. These devices use the law of quantum mechanics, but they don't control individual quantum systems. You cannot control, a normal transistor would not control an individual atom or an individual photon. So the big development of the past 3 decades is the ability to access individual quantum systems, maybe to put them in the state you want and to make the state change in the way you want, or approximately in the way you want. So there have been enormous advances here. Here there are 3 pictures that give you a feeling of some of these advances. Here is a picture of 9 ions of calcium. So each of the little dots here is 1 ion or 1 atom that lost a few electrons. So you can really see that there, and each of them can be addressed individually, and the state of them can be controlled individually, and even their correlations. Of course, this requires you like very low temperature. This is like millikelvin temperatures. These things are inside a trap that uses magnetic and electric fields to keep the ions in the place where they are, but it can be done very accurately. Here is another example of systems where you have a very fine control, is a spin chains. This comes from a recent paper, but there are many older ones. So you can put different molecules next to each other that would have, each of them would have some magnetic spin, and the spins are coupled together in these chains, and this gives rise to a lot of interesting quantum phenomena. Again, you can address the quantum state of very few systems together, and this is the kind of the big quantum engineering advance of the past decades. Here, this is not a picture, this is an artist drawing. It represents a chip for photonic circuits. So these things exist, but I just found that this was clearer, this picture was clearer to show to you instead of just showing a big bunch of devices. So here it means that there are single photons, or approximately single photons, that enter into waveguides and are coupled together, and there are gates that one can operate on them. So it's a very fine-grained control of microscopic quantum systems. And this means that now we are getting the ability to probe experimentally some cause-effect relations between individual quantum systems. And this type of information that we could get would give some useful clue about the devices that we are building. One obvious thing that you may want to do is to verify the behavior of a device that somebody has built, and you would like to test what are the dependencies between the inputs and the outputs of the device. And this is pretty much a problem of causal reasoning at the quantum level. So here I put also a few more kind of technological applications that we could expect in the coming years. The obvious one is to quantum control. You would like to see if acting on some quantum system, maybe on the first spin of a spin chain, can have some effect on other quantum systems, maybe the last spin of a spin chain. Is there a connection between them or not? Can I control that by acting on this? So this is, again, a problem of causal reasoning. Same philosophy also for quantum communication. Imagine that somebody has built a quantum communication network, and you want to know if you can send a signal from one node of the network to another. And again, you want to check if there is such a connection. So testing for a communication link between one place and another is another example of testing for a cause-effect relation. You want to see if your input can change the output on the other side of the network. Now, something that maybe is of a different flavor is the characterization of quantum devices. So we are now in the age of intermediate scale quantum computers and quantum devices. So there are not very big, but not very small either, systems that are being built by companies like IBM or Google that are claimed to be quantum computers and to behave in a certain way. So one question is like, how do you verify, how do you benchmark the behavior, the practical behaviors of the devices compared to the theory that people claim to have implemented? And now checking the behavior of a device is actually pretty hard, because when the device has many inputs and many outputs, it becomes kind of difficult to it requires an exponentially large size of statistics to have a full characterization of the device. But if the device has some simple causal structure, if the causal relations between the inputs and the outputs are relatively simple, then you could characterize them efficiently. So if you are expecting your device to have a certain causal structure, you could first test for it. And if you know that it has that causal structure, you could characterize the device faster. The last application that is very long-term is the one to quantum artificial intelligence. So inspired by what the work of Pearl has been for classical artificial intelligence, we could hope that we could one day design or implement some quantum machines that can learn and exploit some cause-effect relationships that they learn from the environment. For example, a machine that could correct an error inside the computer automatically by detecting it and correcting it. All right. Oops, sorry, the other way. Okay, so what about this quantum cause-effect relations? In a few recent years, several groups have worked on these questions, maybe with different names and with different frameworks. Well, we have been some of the first who have kind of been thinking about these ideas. So there are now frameworks to define what is a cause-effect relationship at the quantum level, and they are kind of, even if the language is different, they kind of agree with each other. On the other hand, what we don't have much nowadays are like algorithms that do the job, that identify the cause-effect relationships with quantum systems. So there has been less development on the algorithmic side of this quantum causality research area. And today's talk, the thing I wanted to talk about, is to talk about this, about quantum algorithms for discovering cause-effect relationships and some advantages that these algorithms may offer. This is mostly based on two papers. One was from 2019, it was Nature Communication, and one is from this year, is Nature part of the journal Quantum Information. All right. So the basic of how to define cause-effect relationship in a general physical theory, like in quantum mechanics, would be this. So you have a variable A, which could be the state of a quantum system. And we can say that this is a visible cause for the variable B if changing the state of A induces some change in the statistics of B. So A is like the knob that allows you to change B. So more formally, this would mean that there is some function, some process P that goes from the state space of system A to the state space of system B. So it tells you how the state of A is transformed into a state of B. And if the output of this process depends on the input, so if this function P is not a constant, if it is a function that has some non-trivial dependence, then you would say that A is a cause for B. For example, so there would be a problem of distinguishing between two hypotheses on the causal structure of a process P. So you could have an unknown physical process, P, that connects a set of variables, of input variables to output variables. And you can ask, what is the internal structure of this process, B? So the causal hypothesis would be an hypothesis on how the inputs depend on the outputs. For example, here you could have a process with 3 variables, 1 input and 2 outputs. You could have that input B depends on so output B depends on the input, but not output C. So C doesn't have any dependence. Or the other way around, you could have the dependence from A to C and nothing going to B. And you may want to test one hypothesis against the other and see which one is right. Yes. So this is the kind of the formulation of the problem of testing causal hypothesis. So your input is that you have a process that you can test, and you have a finite set of hypotheses on the causal structure of this process. And then as an experimental, you can probe this process a few times. You can do some statistics on it. And maybe you can even do some intervention between one trial and the other. And in the end, the output should be a guess for the correct hypothesis. You should find what is the correct hypothesis. So here is a scheme of how this would work. So the process P is used many times, and you could prepare the initial variables in some state, and between one step and the other, you could intervene, do some operation that is your intervention, and in the end, you would measure the output and try to guess what is the relation, the internal structure of this process. So the important number here is the probability to be right or the probability to be wrong. So what is the probability that you get the wrong hypothesis? So this is the probability of error that will depend on the number of trials of the process that you have. And you see, like in the worst case, what is your probability of error? Usually people do a statistical analysis, so they think that this probability goes down exponentially, normally. So the important thing for an exponential is the rate. So this quantity, we take the logarithm, divide by n, would be the exponential rate that for which the probability goes to 0. So this is the key number that you want to look at to understand how good is an algorithm. So an example that I have here is to identify whether a variable is a causal intermediary of another. So there is a variable A, and variable B collects all the possible causal influences coming from A. So it's like you can think of it as a screen through which all the influences of A have to go. So this is what we call a causal intermediary. And one example of this problem would be that you have 3 variables, and you have to distinguish between B being the causal intermediary for A, while C is kind of random, so is independent of A, or the other scenario where C is a causal intermediary of A and B is random. So same picture as before. So no information goes to C here, or no information goes to B there, whereas the other variable is the effect. The causal intermediary means the effect in a very strong sense. So we have to decide which of these 2 hypotheses is correct. And we can compare how well we do this classically and how well we do it in the quantum world. So classically, you would have 3 random variables. Let's say each random variables with an alphabet of size D. Let's say D equal to 2 would be bits. You would have 3 bits. And one hypothesis is that the value of the bit B is some permutation of the bit A. So either B is equal to A for bits, or it is A flipped. So a 0 becomes a 1, or 1 becomes a 0, whereas the other variable is random. Or the other hypothesis is that C is a permutation of A, while B is random. This is the classical case. In the quantum version, you would say that the quantum state of B is obtained by applying some reversible transformation to A. For those of you who know quantum theory, this would be called a unitary evolution, whereas the state of C is random. And the other hypothesis, sorry, this is a 2, hypothesis 2 would be the one where C is obtained from A by reversible evolution and B is random. So what is the classical solution? I think time is running fast, but I would like you to try to guess from this table which of the 2 dependencies is correct. So imagine that, so one strategy would be just to try some value of the input and see what are the outputs and try to see which one is the effect of the input and which one is fluctuating random. Which one do you think is the effect? And which one is fluctuating random? A. And C is doing what? Sorry? C is random, yes, because you see A0, C0, A2, sorry, A0, C2. So it's if they were a kind of permutation, it should be just the mapping 0 to 0 and 1 to 1. But then you get here a 0 becomes a 1. So it cannot be a kind of a deterministic function. So C should be the one that is fluctuating at random. And so what is your probability of error? Well, if you compute the probability of error of this simple strategy, you find that the error happens when both tables are accidentally compatible with some invertible function. Then you cannot decide. So in that case, your probability of error is 1/2. So the total probability of error is the probability that you are unlucky, that you cannot tell, divided by 2. And the calculation gives you this, 2 divided by d to the power n minus 1. Right, so if you compute the rate, the exponential rate of decay of that probability of error is the logarithm of d. This is the speed at which the error probability goes to 0. And this is actually the best over every possible classical strategy that you can think of, not just the one that I mentioned. Now, let's see the quantum solution of the problem, and let's see how well can we do there. Now, a simple quantum strategy, for those who know quantum theory, of course, is to try to divide all our input variables in groups of d. So if your systems have 2 levels, you would divide the inputs into groups of 2 and prepare some special entangled state, some state that has this strange property. This is called, this particular state that we use here is called the singlet state. And I guess you have heard of that, no? So this is the state when you in high school, you learn about the electrons that are anti-parallel with the exclusion principle, you know, that one spin is up, the other is down. Actually, the true state of the electrons in high school chemistry would be this one, the singlet state. So for d equal to 2, this is just the state where, let's say, one spin is up and the other is down, or vice versa. They're kind of superposed coherently together. These two situations coexist together. So one strategy is just to divide the particles in groups of 2, let's say, for dimension 2, and to prepare them in this way. So if you do all the calculation, you find that the probability of error has this value, 1 divided by 2d to the power n, which is a tiny bit better than the classical probability of error. There is just a factor of d, but the rate is the same. So we haven't gone very far. The rate is still logarithm of d. So question is, can we do better? And of course, the answer is yes. And the interesting quantum idea here is, how do we do it? So you saw that in that strategy, the best you could do was to divide the inputs in groups of 2. Yes, and to connect them in pairs. So, but of course, there are many ways that you can do that. You could create a singlet between the first and the second particle, between the second and the third, the third, the fourth, and sorry, because the third and the fourth, and the fifth and the sixth. Or you could create a singlet between the first and the third, the second and the fourth, and so on. So there are many ways that you can group these particles together. And all these strategies experimentally would be equally good. Each of them would give you exactly the same probability of error that I showed to you in the previous slide. Now, the crazy thing in quantum theory is that you can use all these strategies at the same time. So you could think of building a setup where you either prepare, you group the inputs in this way, and you have a control variable that chooses how you group them. And you could superpose, create this coherent superposition where you group them in another way at the same time, and in another way, and in another way, and so on. How many do I have? 5, I think. Yes. So this is a bit like the famous Schrodinger's cat, where there is one control variable, like one particle, that controls whether the cat is alive or dead. So here is not so cruel. The control variable only controls how we group our inputs when we test this process. So for those who know, so what you would get would be this sum is a sum of vectors where some vectors correspond to the different groupings and some other vectors correspond to the control variable. If you do all the calculation, you find out the probability of error goes down exponentially faster now. So this thing that seemed completely innocent, like putting together setups that are equivalent, actually made your probability of error exponentially smaller with the number of trials, which if you look at the rate, this means that the rate is doubled. So that the speed, exponential speed that the error is going to zero is double the one you have in the classical case. Okay, very nice. So this tells us that there is a quantum advantage between the classical version of the problem and the quantum version. So we double the rate. Sorry, we double the rate of the discrimination between these two hypotheses. And this advantage is obtained in this very quantum way of superposing many alternative configurations. Okay, so this is very nice, but this is very theoretical. I mean, this is very idealized with these perfect permutations. So after that, we looked into some noisy version. And I will just go fast on this. I don't have too much to say, actually. So the idea here is that we cannot just promise that our process is a perfectly reversible process or an invertible function. There will be some noise in the process. So the general question is, imagine that you have some big noisy process with many inputs and many outputs. And inside the process, these inputs interact in some way that you don't know. For example, the first input 2 and input 3 could interact together, produce output 3, and produce some intermediate product that interacts with input 1 and gives you output 1, and so on. So there could be some complicated structure of interactions inside your device, but you cannot look inside. So you would like to find out, just from the input-output behavior, what is the internal structure of this device. This could be a chemical reaction, or it could be a nuclear reaction where you see only the input product, the inputs and the output products. So how can you unravel the internal structure? And this was a problem, again, of causal characterization. Previous results required a full characterization of the input-output behavior, which cannot really be done because this is the behavior is exponentially complex. So this would require an exponentially growing statistics. And basically, our result was that we found the first protocol that is not exponentially complex, that has a complexity that grows in a rather benign way. Well, I don't know how would you call it, but it grows like the cube times the logarithm of the number of inputs and outputs that you have. For computer scientists, this is good. This is called it's kind of polynomial scaling is good. It's not exponential, and so we are happy. And this works under some reasonable assumptions. All right, with this I'm done. So in summary, which I will not repeat, so we had this framework for causal relations, and I showed you some simple algorithm that exhibits a quantum advantage, and also kind of more general technique that can work in the noisy cases. The big open question is how many experiments, how far can we push the kind of the practical and experimental demonstration of all these ideas. So far, there are a few experiments, but not so many. So we hope to see more in the future. I'm done. So thank you very much for your attention.